Hello, everyone. This is Shiqing Fan from Alibaba Group. Today, I am excited to talk about our work. DAPPLE, a pipeline data parallel approach for training large models. Nowadays, modern deep neural networks are becoming extremely large, and training large DL models on sophisticated GPU platforms is challenging. On one hand, model and data parallelism often suffer from high communication overhead and low resource utilizations. On the other hand, inter- and intra-node connect capabilities are diverse. For example, the following table shows 3 typical hardware configurations in Alibaba Group, where config A represents hierarchical interconnections, and config B and config C are flat configurations. Recently, pipeline parallelism has been proposed as a promising approach for training large DNN models. The idea is to partition model layers into multiple stages and place them on a set of machines. During training, each input batch is further divided into multiple micro-batches, which are scheduled in to run over multiple devices in a pipeline manner. Parallel research on pipeline training generally falls into 2 categories. One is on optimizing pipeline parallelism for synchronized training. GPipe from Google is an example of integrating data and model parallelism. GPipe is a distributed machine learning library that uses synchronized mini-batch gradient descent for training. It only needs to preserve single weight version. The key idea of GPipe is that it divides the data mini-batch into micro-batches. And then different devices work on different micro-batches at the same time. These workers sync up at the end, and the gradients are updated when the entire mini-batch is processed. Gradients are consistently accumulated across micro-batches so that the number of partitions does not affect the model quality. However, this partition algorithm of GPipe is simply heuristic-based, and each device simply schedules all the forward micro-batch before any backward starts, which makes worse peak device memory. The other category is asynchronous pipeline training. PipeTrain from Stanford and CNU is a representative work of asynchronous pipeline training. This method inserts micro-batches into pipeline continuously and discards the original synchronized operations to achieve maximum throughput. Although these efforts have made good contributions to advanced pipeline training techniques, they have some serious limitations. While PipeTrain made progress in improving the time to accuracy for some benchmarks with async pipeline parallelism, async training is not a common practice in important industrial application domains due to convergency concerns. This is reflected in characterization study of widely diverse and fast-evolving workloads in industrial-scale clusters. In addition, the async approach requires the storage of multiple versions of wait and activation. This is a must in async training to ensure same weight versions used in both forward and backward paths. This, while friendly for increasing parallelism, further accelerates the already critical memory consumption issues. So, can we achieve both high throughput and low memory footprint for synchronized pipeline on sophisticated GPU platforms? In this paper, we propose DAPPLE, a distributed training scheme which combines pipeline parallelism and data parallelism to ensure both training convergency and memory efficiency. DAPPLE adopts asynchronous training to guarantee convergency, which avoids the storage of multiple versions of parameters and activations in asynchronous approach, just like pipe dream. Specifically, we address two design challenges. First, the first challenge is how to determine an optimal parallelism strategy given model structure and hardware configurations. We propose DAPPLE planar, and DAPPLE planar combines pipeline parallelism and data parallelism together while partition layers into multiple stages. As well, our DAPPLE planar will generate optimal parallelism strategies automatically by minimizing execution time of training iterations. The second challenge is how to schedule pipeline stage computations in order to achieve a balance among parallelism, memory footprint, and execution efficiency. Our DAPPLE runtime schedules forward and backward stages in a deterministic and interleaved manner. Experiments show that our DAPPLE runtime consistently outperforms pipe dreams planars in async training scenarios. This figure shows high-level workflow of DAPPLE, which features a profiler, a planar, and a runtime system. Overall, DAPPLE profiler takes one DNN model as input and profiles execution time, activation sizes, and parameter sizes for each layer. Taking profiling results as input, DAPPLE planar generates an near-optimized hybrid parallelism plane on a given global batch size. Both DAPPLE profiler and planar are offline and can be complicated in a few seconds for all of our 6 benchmark models, which will be introduced later. Finally, our DAPPLE runtime takes the planar's results and transforms the original model graph into a pipeline parallel graph. At this stage, global batch size is further split into multiple micro batches and then being scheduled for execution by DAPPLE runtime. We design and implement DAPPLE runtime in TensorFlow 1.12. As common practice, TensorFlow takes a precise and complete computation graph, schedules and executes graph nodes respecting our data dependencies and control dependencies. The first table summarizes all the 6 representative DNN models that we use as benchmarks in our paper, and table 2 summarizes 3 common hardware environments for DNN training in our experiments, where hierarchical and interconnections and flat interconnections are both covered. In general, hierarchical interconnection is popular in industrial GPU data centers. We also consider flat Ethernet networks because read-only link may not be available, and GPU resources are highly fragmented in some real-world production clusters. Let's give some quick results about DAPPLE comparison with gpipe. This figure shows how the memory consumptions change over time in gpipe and DAPPLE. The number in the cell represents microbatch IDs. To improve pipeline training efficiency, gpipe proposed to split global batch into multiple microbatches and inject them into the pipeline concurrently. However, this scheduling pattern alone is not memory-friendly and will not scale well with large batch. The activations produced by forward tasks have to be kept for all microbatches until corresponding backward tasks start. Thus leads to the memory demand to be proportional to the number of concurrently scheduled microbatches. gpipe adopts recomputation to save memory, while bringing approximately 20% extra computation overhead. In DAPPLE, we propose early backward scheduling strategy to reduce memory consumptions while achieving good pipeline training efficiency. The key idea of early backward scheduling is to schedule backward tasks earlier and hence free the memory used for storing activations produced by corresponding forward tasks. The last figure 3C shows how the memory consumptions change over time in gpipe and DAPPLE. At the beginning, the memory usage in DAPPLE increases with time and is the same as gpipes until 3 microbatches are injected. Then it reaches the maximum due to the early backward scheduling. Specifically, with strictly controlling the execution order of forward and backward stages, the occupied memory for activations produced by the forward of a microbatch will be freed after the corresponding backward, so that it can be reduced by the next injected microbatch. In comparison, gpipe's peak memory consumptions increases continuously and has no opportunity for early releases. Moreover, DAPPLE does not sacrifice in pipeline training efficiency. This table shows the performance comparisons with gpipe. We focus on the throughput and the peak memory usage on BERT with 48 layers with a 2-stage pipeline in config B. Config B is a flat configuration. To align with gpipe, we adopt the same recomputation strategy, which stores activations only at the partition boundaries during forward pass. When both without recomputation, DAPPLE gets about 1.6 speedup on throughputs and save about 13% memory consumptions. The speedup from DAPPLE is mainly because higher microbatches leads to lower proportion of bubbles comes from the pipeline. It should be noted that DAPPLE allows small microbatches as the peak memory requirement is independent of number of microbatches due to early backward scheduling. The combination of DAPPLE scheduler and the recomputation allows a further exploration in memory usage. Compared with baseline of gpipe, DAPPLE plus recomputation achieves 1.22 speedup on throughput and saves about 36% memory consumptions. We also compare the results of our DAPPLE planner with those of pipe dreams under the synchronized training scenarios. We use the same configurations for both planner. For example, same device port C, same interconnect, and same profiling data, and evaluate both planners with DAPPLE runtime. Here we take both large planner results as an example. This is the first pipeline, and this is the second pipeline. This mapping explores workload characteristics by leveraging the high-speed NVLink for heavy gradient sync, while using the slow Ethernet bandwidth for small activations communication. This figure shows the performance results for the strategies running on both 2 servers and 4 servers, with each server with 8 devices. From this figure, we can show that DAPPLE planner consistently outperforms strategies generated by pipe dreams planner by up to 3 points and 23 speed up on the synchronized training scenarios. Then let's show some large model scalabilities. This table shows the maximum model size that DAPPLE supports on the reasonable input size with recomputation enabled. We scale the model by varying the number of layers. We are able to scale BERT to 5 billion on 8 Volta GPUs with NVLink enabled. There is a slight reduction in average GPU utilization due to more bubbles introduced by longer pipeline stages. In this case, the maximum model size scales linearly due to the balanced distribution of model parameters over encoded layers in BERT model. Here are more DAPPLE planner results. This table summarizes DAPPLE planning results of 6 models in the 3 hardware environments, where the total number of available devices are all fixed to 16. The first column of this table also gives the global batch size correspondingly. Due to the time, the details will not be expanded here. There are also many more interesting details in our work. For example, uneven pipeline partitioning with fewer stages and versatile device placement strategies in DAPPLE planner. There are also some trade-offs in design DAPPLE planning algorithms. These and more can be found at our poster. So let's give a summary of today's talk. In this paper, we propose DAPPLE framework for pipeline training for large DL models. DAPPLE addresses the need for synchronized pipeline training and advances current state-of-art by novel pipeline planning and microbatch scheduling approaches. On one hand, DAPPLE planner automatically determines an optimal parallelism strategy given model structure and hardware configurations as input. On the other hand, DAPPLE scheduler is capable of simultaneously achieving optimal training efficiency and moderate memory consumption without storing multiple versions of parameters and getting rid of strong demand of recomputation, which hurts system efficiency at the same time. Thank you.